Welcome to the last video of the fluid at rest, where we will study the effects of fluid compressibility. To do this, we will no longer assume that the compressibility parameter K is small. On the other hand, we will neglect the viscous effects and thus make the Stokes number tend to infinity. Let us take our schematic view of the fluid structure interaction and assume that Stokes number is very large. We then simplify the momentum equation by neglecting the viscous terms once again, and we notice that the equation describing the stationary state is independent. We can therefore set it aside for this study. Since we are dealing with an inviscid fluid, it is again possible to transform the kinematic condition by being interested only in the normal velocity, since sliding is allowed. We can now derive with respect to time the first equation, which is the mass conservation, and take the divergence of the second equation, which is the momentum conservation. This gives us the possibility to replace the divergence of du prime over dt by the Laplacian of p prime in the first equation. We are now only dealing with the pressure. Then we use the momentum conservation to make the pressure appear instead of the velocity in the kinematic condition after it has been derived once with respect to time. We obtain a set of equations that deals with the pressure field and that is finally the same as when we studied the inertial effects, with just one more term related to the compressibility. The equation that governs the pressure is now the classical equation of linear acoustics in fluids. When we coupled acoustics with structural vibration, we study vibroacoustics. In this video, we will highlight the main phenomena by considering a very simple structural movement. It is the motion of the pulsating sphere. We can describe this motion with a deformation mode equal to ER on the interface and a dimensionless frequency equal to 1. Everything is unitary here because it is the oscillation frequency and the radius of the sphere that have been used to scale the time and the length. By transferring this simple displacement field into the kinematic condition and noting that the normal to the interface between the fluid and the structure is ER, we obtain a condition on the derivative of the pressure fluctuation with respect to R at R equals 1. Let us now solve this problem. We will look for a solution with separate variables which takes into account the symmetries and parameters of the problem, that is a product of a function of r and a function of time equals to e to the minus it. The wave equation in a fluid is transformed into an equation which only deals with phi p. This is the Helmholtz equation. Since phi p depends only on r, we find a simple differential equation whose general solution is the following. It is the sum of two functions of the form 1 over r times a complex exponential. The pressure then takes the form of a sum of two wave solutions whose amplitudes varies as 1 over r. The first wave, in view of the presence of minus k r minus t, is a wave propagating from infinity to the origin. In the problem that interests us now, it has no physical existence since there is no acoustic source other than the pulsating sphere. The second wave propagates from the origin to infinity. It is the wave that is actually generated by the pulsating sphere. We therefore retain only this solution for the rest of our analysis. It remains for us to evaluate the constant B. For this, we use the condition at the interface d omega naught, where dp prime on dr equals 1. Once this work is done, we finally obtain this expression for the pressure fluctuation. We can now project this pressure onto the displacement mode ER at the interface. This calculation gives us a force equal to 4 pi e to the power minus it over 1 minus I. Let's put this force back into physical units. By doing this calculation and rearranging the terms, we finally show that the coupling with the acoustics induces a force proportional to the acceleration and a force proportional to the velocity. That is to say, an added mass and an added damping. The added mass is 4 pi rho r cubed over 1 plus k squared. We see that the added mass tends to a constant for small k. This constant is what we would find if we did a calculation of added mass with the assumption of incompressibility. Recall that K is equal to omega naught R on C. We can deduce the typical evolution of the added mass coefficient as a function of frequency, which is represented here graphically. We have also highlighted an added damping coefficient, which can be plotted as a function of frequency. We notice that this coefficient follows the opposite trend. We can distinguish two different regimes in this fluid structure interaction problem. In the first regime, at low frequencies, the solid carries a small layer of fluid with it, but does not efficiently radiate acoustic waves into the external fluid medium. This results in an added mass determined by the small fluid volume that follows the sphere in its oscillation, and a low added damping since little energy is transmitted to the outside. In the high-frequency regime, on the contrary, the fluid layer that follows the solid is very thin, and the added mass decreases. On the other hand, the radiation is efficient, and a lot of energy is transmitted to the fluid without being returned, and consequently, the added damping is important. It should be noted that in the acoustics community, this dynamic interaction between the solid and the fluid is best represented through a number called the radiation impedance, which is the ratio between the pressure and the velocity at the interface. In this framework, the added mass is proportional to omega naught times the imaginary part of Z, while the damping is proportional to the real part of Z. This brings us to the conclusion of the last video in our series of oscillations of structure in the fluid at rest. We have demonstrated vibroacoustics concepts and phenomena on the simple problem of the pulsating sphere. The acoustic radiation has been calculated. We have highlighted an added mass and damping. The fundamental parameter that quantifies these quantities is the compressibility parameter. For those who would like to make the link with the acoustics literature, this parameter can finally be seen as the product of the wave number and the characteristic size of the radiating source. It is often called Ka. We could now address the radiation of different sources, no longer having spherical symmetries. The calculation would be more complex. We will introduce the notion of directivity of the source, that is, a radiation that depends on the direction, but the physics would be unchanged. Finally, it should be noted that we have just studied the coupling between a vibration and waves propagating in an infinite space. One could also consider the finite fluid medium. In this case, the modal approach would be more relevant to describe the physics of the fluid medium. We would then deal with the coupling between the structural modes and the acoustics modes. We would then have to draw inspiration from the modeling approach we have done from the coupling between free surface mode and the modes of the tank. It was done in video 3.1. That's it for this week. See you next week. We'll be able to discuss fluid structure interaction with flowing fluids.